Hi, everyone. I took someone else's laptop from my last section, and someone took my laptop. So I won't be live coding today. Instead, I'll be writing code on the whiteboard. I'm sorry. Well, actually, nah, that's not ethical. All right, never mind. I'll just live code. All right. So yeah, today we're going to do binary search trees, and let's just get started immediately. Please, is it Netta? No, it's not. Okay, let's get started. So let's say, is that possible? Okay, can it connect? Yes, it does. Well, actually, no. No, it doesn't have HDMI. Does that have HDMI? Type C, yes. Okay, okay. All right, thanks so much. Back here? Okay. All right, so. Okay. Do you mind opening your email and going to that link? Actually, no. Okay, it's fine. That's fine. I'll just open code. All right, sorry, y'all. I took the wrong laptop. Let me just use. All right. Let's start with height. Where's height? Height. Hi. My bad. Here you go. Yeah, I was wondering why my laptop suddenly turned into a MacBook Pro. Thanks so much. And yeah, thank you. Thanks to you too. All right, here you go. All right. So I've section led for 8 quarters. This has never happened before. So yeah. Okay, back to normal. How much time do we waste? 5 minutes. Okay. Let's cover 4 questions instead. All right, so height. All right, let's get started. So suppose you were given a tree. We were given a tree, 7, 4, 8. 7, 4, 8. 2, 1, 3, 5, 6. 2, 1, 3, 5, 6. Okay, and then this is a binary search tree, and we want to find the height of the binary search tree. Okay, this is question, I think question 2. All right, so for example, what is the height of this tree? So some places define this as 4, some places define it as 3. I think with the definition we're going to use I think it's one written on the handout, we're going to use the definition longest path from the root to a leaf. Okay, we're going to use that definition. So using that definition, what is the longest? What's the height? 3, right? 3. So we start here, 1, 2, 3. All right, and then essentially we want to write a function which helps us determine that. Okay. Now, binary search questions are almost always inherently recursive. So we want to do the same thing we did when we were learning about recursion, which is looking at the root node. Think about how the root is related to its children. So in this example, we want to think about how the height of the root is related to the height of its children. Okay. So quick question: what's the height of this child? What's the height of the tree starting at this node? 2. Okay. And how about this one? 0. Okay. Any ideas how the height of the root tree is related to the height of the subtrees?
larger height than the one.
Yeah, exactly. So the height of the larger tree is the larger of these two values plus 1. Okay, which would make sense because, I mean, the reason why this is 2 is because the longest path, let's say this path, let's use the longest path is this one that has length 2, right? So to get the longest path starting from 7 to the root, you would just add that one segment. So it's always whichever one is larger plus 1. Does that make sense? Okay, let's quickly code it up. So since it's recursive, we want to think about what a base case would be. What would a base case be in this recursion? When can we no longer make smaller and smaller subtrees? Yeah. Great. So if node equals nullpater, then what would its height be? 0. Yeah. Exactly. So we'll just return 0. Well, actually, is it? Yeah, we should.
Have a height of 1.
Okay, that's a good point. What does the height say? What does it say? It says we want the height to be empty tree has height 0. Tree of node. Oh, I see. Okay. So we're not doing. My apologies. We used the wrong definition here. The real definition we want to use is an empty tree has height 0. So this node itself has height 1. This node has height 2. Like this has height 2. This is height 3. So this whole thing has height 4. Okay? Yeah, my apologies. We used the wrong definition here. In some places, the definition that's used is the empty tree is -1, which doesn't make a lot of sense. But in this example, we're going to use the definition that it's the number of levels you have. So that would just be 1, 2, 3, 4. Okay? Yeah, thanks for pointing that out. So in this example, if it's a null pointer, then we just return 0. Otherwise, how do you calculate the height of the entire tree?
You can do return and then whatever, which one is bigger between the children plus 1.
Okay. How do we find the height of the children?
Do it recursively, so call it for each one.
So node on the left, and then height of node on the right, and then we want to find whichever one is larger. So let's just do max of that plus 1. Okay. Run the code, and it works. All right. Any questions? Great. Let's move on. Is balanced. So what's the definition of a balanced tree? Yeah, so it's if the heights of the children differ by at most 1. Okay, so for example, in this case, this is not balanced because 3 and 1 does not differ by at most 1. Okay, now something you want to think about is even though we can just check here, we want to check the root if the root is the same. What if we had a case like this? So 7, 4, 8. 3, 2. Then, let's do 9, 10. So this tree is not balanced. Is this tree balanced? Let's see. So, okay, why is this tree not balanced? So notice here, if we think about what the height of the two children are, it's 3 and 3. But this tree is still not balanced. All right, why is that balanced? Yes? Yeah, exactly. So to check if it's a balanced tree, we not only have to check this condition for the root, if its two children differ by at most 1, but we also have to check that for every other root in every other node in the tree. Okay. After you're done checking the root, then you have to check, okay, is the tree starting at this root balanced? No, it's not because this side is 2, this side is 0. Okay. So how can we, if you had to rephrase that in terms of like whether or not this is a balanced tree, the entire tree is a balanced tree if these differ by at most one, and one more condition. What has to be true about this tree versus and this tree? Mm-hmm.
They have to be balanced.
Yeah, that's a balanced, exactly, right? Because that same thing we said about you also have to check all the other conditions, right? All like this tree also has to have difference of at most one. That's the same thing as saying, oh, this tree has to be balanced and this tree has to be balanced. Okay, you can see why tree questions are often recursive. So let's just quickly code it up. Is balanced. Let's see, what would a base case be?
No pointer.
Yeah. Mm-hmm. On tree questions, you can always guess the base case is probably null pointer. All right. So if it's a null pointer, then is it balanced? Yeah. I think it's technically balanced. And then if it's not a null pointer, then how do we check if it is balanced? Yeah. Mm-hmm.
You call it recursively, so if is balanced node points to left children.
Mm-hmm. So we call it is balanced on the left. Okay.
And
Mm-hmm.
is balanced nodes right.
Okay, so we need to call is balanced. We want to make sure both the left and right subtrees are also balanced. Great. And then there's one more condition we have to think about, and that's the threes up here. Right? We have to make sure that the original tree we started at the root, we have to make sure that the heights of both children are also differ by at most one, right? How do we check if these differ by at most one? I'll give you a hint. We just wrote a function which finds the height. Yeah. Mm-hmm.
We store the height in the data.
Sorry, can you say that one more time?
Mm-hmm. The tree node variable data.
Mm-hmm.
Can we store the height in this?
I prefer not to because then that actually changes the 7.
Oh.
Yeah. I don't think we have to do that because we can. How would you calculate the height of these two subtrees? Yeah. We just wrote a function called height, so we can just use that function. Yeah. So height. We calculate the height of the left subtree, and then we also calculate the height of the right subtree. And what do we do with this value? Sorry. Yeah.
Oh, just compare them.
Compare them. Okay. And what do we want to make sure about these two values?
Subtract like the right from the left.
Mm-hmm.
Like the absolute value has to be less than or equal to 1.
Sure. So let's just say absolute value of that. So then to determine if the entire tree is balanced, we're checking if the left is balanced, if the right is balanced, and if the absolute difference is less than or equal to 1. Just return that. And, oh, what? It does not recognize height. Does it not recognize height? Great. Okay, well, you know what? Let's just take this function, copy paste it over there. Ta-da! Okay, there we go. Any questions? Yes?
Is it worth it to like on large tree to like define it so that if the difference is greater, then you just cut it off and return false rather than going on to still check if like the subtrees are balanced?
Yeah, that is a very good point. So one thing you could do over here is instead of putting it at the end, you could put that at the beginning. So what happens here is if the difference is not less than or equal to 1, then we just short circuit because it's an and. So if this is false, then we're going to return false anyways. We just stop. Okay, so this is slightly faster, I think. Yeah. Okay. Yeah. You also bring up a good point about like inefficiency. This algorithm we wrote is not really efficient. right? Because we're calculating height many, many times below, right? At every step, like when we make a recursive call, we're going to call height again on here and here. Recall from the previous function that all the heights are kind of related. All the heights, you can easily find the height of one tree based on what the height of another subtree is. Any ideas as to how we can make like the height function a little bit more, how we can make this a little bit more efficient? We can use the technique Tyler talked about a couple weeks ago called memoization, which is we use a map to essentially store what the heights of various nodes are, and then in the future, if we ever have to calculate that again, then we don't have to make a recursive call to figure everything out. We can just look at the map to see what was there. Essentially, as you're doing work, if you get some results of what height is going to return, then store it into your map, and then you never have to calculate it again. Does that make sense? Okay, you don't have to know that for the exam, but Tyler did teach you that 2 weeks ago. Question, yeah?
Let's say from the right graph, so we're stepping from 7 to 4 at first, right? So at 7, the height is 4. And then when we just step one step, so you can just say 4 minus 1.
Mm-hmm.
And then you say, when it goes from 4 to 3, you just say the height will be 3 minus 1 equals to 2.
Uh-huh.
So you don't need to use a temporary variable. You just say 3 minus 1. So you know the height of node 2, node 3.
Okay, that's an interesting point. I think it worked for this one, but for this one, like one of the trees will work for sure. So like 4 goes to 3.
Yeah.
But the other one might not work because we're finding whichever is the max plus 1. Yeah, but I do think you bring up a good point, which is there's probably some way you can do so. Like after you get the heights of these two, you don't forget the 1, and then you can just when you make the recursive call, know that which one's the 3, which one's the 1. That might help as well. Okay. There's also one more way you can do this called dynamic programming, but you don't have to know that for the exam as well. Okay. All right. Great. Any questions so far? Okay. There's a question called is balanced. No, actually, there's a question called is BST, but my previous section had a lot of trouble with this question. So instead, what I'm going to do is I'm going to do remove leaves first. Then I'm going to go to the exam question, and then we'll come back to this question. Okay. If you're interested in anything related to artificial intelligence, there's this technique called alpha beta pruning, and they use this technique to solve chess. Not solve chess, to write a really good program which beats all human players in chess. And the one technique they use is called alpha beta pruning, which is kind of what we would do for question 5, is BST. My last section had a lot of trouble with it though, so I'm going to skip it for now, and then we'll come back at the end. Okay, let's do remove leaves. Remove leaves. Okay. Question is simple to describe. Okay. Remember what the definition of a leaf is? The definition of a leaf.
Has no child.
No children, exactly. So in this example, what would the leaves be? 1, 3, 6. Anything else? And the 8, right? Because the 8 has no children too. Okay. So what we're going to do in this function is we're going to essentially go through the list and delete, or rather remove all the leaves, and also free all their memory. Okay. So after this function's done, we should not have these nodes anymore. Make sense? Okay. So to remove the leaves, we have to find a way to go through the function and figure out where the leaves are. How can we identify if we're at a leaf? Sure. Okay. So we know that we're at a leaf. We are at a leaf if the left pointer is nulliter and the right pointer is nulliter. Okay. So that is how we know we're at a leaf. If we're at a leaf, so let's say we're at this leaf, right, how should we free this node? How can we remove that node? Yes?
We have to set the one above it onto a null pointer, and then we have to delete it.
Okay, yeah, that's great. Let's say delete first. So delete root. So remember that root is pointing to this one. So when you say delete root, oh yes, I always use node root, but they like to use node. Okay, so node is pointing to here, to the 1. Remember that I saw a lot of Piazza questions on this, and I think a couple of you emailed me. When you say delete, you call it on a pointer, but the thing that you're freeing is not the pointer itself. You're freeing what the pointer is pointing to. Okay, so for example, if node is a pointer which is pointing to the 1. In that case, when you say delete node, you're not doing anything with this variable itself. You're freeing what that pointer is pointing to. So you're deleting the 1 itself.
To null pointer when you're done, or does it not matter?
The order in which you do this in this example does not matter. Yeah. So you bring up a good point, which is you always want to be careful when you call delete. You have to be careful of which ones you're be careful if you're ever accessing garbage values. But in this case, you bring up a good point, which is node in this example, because we're passing node by reference. We're passing node by reference. So what that means is if you make any change to node, that actually changes whatever you passed in as a parameter. Okay? And what did you pass in? Later on, we're going to put the recursive call. What recursive call was made to let the function start moving to the 1? Yeah, there you made a recursive call here that said recurse on node left. So you were recursing on this pointer. This pointer. So this pointer itself is node. Okay? So when we say delete node, we're saying, okay, whatever node is pointing to, delete it. So that does this. Okay, and then after we say delete node, we have to make sure that this child is not pointing to garbage values anymore. And as you just said, we would say node equals null pointer. Null pointer. Okay, so because node is passed by reference, we're actually changing this red arrow itself, and we're saying, okay, change that red arrow so that it's not pointing to anything anymore. So this is gone, and this is deleted. Okay, does that make sense? Any questions so far? So yeah, so this is a question. Okay, this is a tricky concept because this is a little bit different from last week when we did the James Bond analogy, right? You had to be standing on the previous node to be able to change that pointer that's pointing to the next one, right? You've been doing this on tiles. You had to be standing on the previous one to be able to change that pointer of the node that you're removing. But when we're doing this recursively, because you're passing the parameter by reference, what happens is that you actually can directly change this pointer even if you're standing here. You don't have to be standing here to change that pointer. You can be standing here and change node directly. Does that make sense? Any questions? Okay, great. And then if we're at a leaf, then we don't want to make a recursive call because there are no more nodes below. So return. Okay. If we are not at a leaf, what should we do? So if we're standing like here, what should we do? Yes.
We did. Go ahead.
Yep. Go ahead. Yeah.
Mm-hmm. Yeah. Okay. You call remove leaves for the left node. You call it for the right node.
Yeah, exactly. So if we're not at a leaf, then you don't have to do anything with the for. Just remove everything from the left and the right. Remove the leaves from the right and the left. So just make the recursive call. Remove leaves from node left, and remove leaves node right. Okay. If we're gonna miss one case. Oh, what? We missed more than one case? Okay. We're missing one case, and that's remember if node is null pointer, then you always have to catch that case. So if null is null pointer, then just return. Okay. Yay. Okay, any questions so far? Let me put the code in right now. Any questions we have right now? So a lot of the code that we're going to write in this class is going to be whatever node we're standing on, do something with that node if necessary. Otherwise, make 2 recursive calls. Okay, questions? If you don't have any questions, take a look at the handout I sent you all. It's a question called, we're going to do the question make full. And actually, instead of reading the handout, it's not on the handout I passed out right now. It's in the email I sent 2 days ago. But if you don't have it, that's fine. Let me just write out an example so we can see what's going on. This is a very tricky question. It's on code step by step. It was also like a past exam question. This is considered like a very tough exam question. Okay. I sent you another code step by step question. That one is a killer exam question. Okay. That one's called stretch, which is very tough. So let's see. We have a tree. Let's not copy that tree. Let's copy the tree out above. So we have one tree, which is 12 to 29. This is one tree. And then let's use the tree below. 12, 28, 94, 65, 94, 65, 18, 19, 32, 19, 32, 72. Okay. So what we want to do in this question is we want to make this tree complete. What does it mean to complete a tree? That means make sure that all the nodes have either 0 or 2 children. Okay? So, for example, these nodes, they have 0 children, so that's fine. This has 2 children, so that's fine as well. But for some of these nodes, like this one and this one and this one, they have 1 children. So we want to fix that. Let's look at the small example over here. This node has 1 children. So what we should be doing is we have to look at which level that this node is appearing. So it appears at level 1. Okay, we're gonna turn this node so that this is a -1, and we're gonna make whatever children that's missing, make that the original root node itself. Does that make sense? Okay, now what's the tricky part about this question is that given this thing, you're not just allowed to say, okay, take the 12, turn its data field so that its data field is now -1. Okay, you're not allowed to do that. Instead, what you have to do is you have to reuse the 12 that was up here. Okay, you can't just change this to -1. You have to move this 12 so that the 12 is now here instead. Okay, so what has to happen is you're going to have to reroute these pointers by first creating a -1. So I'm going to create a -1. Then I'm going to route this pointer to here, this pointer to there, and then remove this pointer over here. Okay, you're not allowed to change the data field. You have to move the 12 so that it's in the right place. That's what makes this question really tough. Okay, so let's walk through this together. What would happen if we tried to do that with 32? Let me just draw it larger. So 32 and 72. Okay. What do we have to do with the 32?
First create node -2.
Okay, so we create a node -2.
And how like right pointed to 72
Okay, so we want to right point this to here.
and left point.
To here. We want to delete this pointer. Okay. And then we want to reroute this pointer so that it points to here. Okay? Tricky. All right, so yeah, this is a very tough question. So let's try tackling it now. So imagine we're going through the entire tree. How do we figure out if we have to do an operation like this? Right. Where in the tree do we do that kind of operation? You do that operation when you have exactly one children, right? As you're going through the tree, if you find a node which has exactly one children, then you have to do that swap. How do we check if it has one children? Can we use what? XOR. We could, but the issue is because whether or not the missing child is left or right, it's hard to combine those together because then you have to we'll be doing a lot of like node arrow left, node arrow right, and it's hard to like unify that into like a common code. So it's easier if you separate into like, okay, if we have one children and the missing child is either on the left or on the right. Yeah, if you use XOR, that unifies them together, but then because the left and right cases, you have to handle them separately. So let's just deal with them separately, okay? So yeah, how do we check if we only have a left child?
If node dot left not equals not null pointer,
Okay,
and the right node does equal null pointer.
great.
It's not a root.
Oh, now it's root. Check plus for consistency. All right. So yeah, root left is not null pointer and root right is null pointer. Okay, so that's one case, and then the other case is the same thing but the other way around. So this is if we only left child, and then this is only right child. Right is not equal to null pointer, and root left is equal to null pointer. Then this is only right child. Okay. All right, cool. So let's say, suppose we only had a left child. So that would be this case. Okay? Sorry, other way around. That would be this case. What kind of pointer gymnastics should we be doing here? What's the first step? A new node, right? Okay, so we're gonna create a new node. What should its value be? Right, it should be the negative of the level right now. We don't have access to that. Right, we don't actually know what level we're on right now. How do we figure that out? How do we get around that? So remember, in recursive functions, if you ever need to pass around extra information, but yeah, we'll make one more parameter. Yeah, exactly. And then that parameter, because we can't change this function itself, we have to make a helper function. Okay. Remember in when you did backtracking, if you ever needed like an extra data structure, you would make a helper function. So let's just copy this whole thing into our data structure, our int make full helper, binary tree node, root, and int level. Okay. Oops. And then we would just copy paste that there. All right. So now that we have the level, we can create a new node with that level. Yes, question?
You just make the int level inside the function of make full, and then you say int level equals to 0. Equals to.
Oh, you want to use default values?
Yeah.
Yeah. I don't. I think don't change the function prototype that is given. Yeah. Just it's just good practice because usually what happens is someone asks you to write this function and they're going to expect to call it that way, and then a better way to explain this is this relates to the idea of like information hiding. You don't want whoever's calling your function to be able to call your that function using like a different level, right? They should only be able to access the function call with level 0. Yeah. So it's just kind of like information hiding. We don't let whoever's calling our function, the client, be able to put whatever level they want in there. Okay. All right. So here we have. Let's deal with the left child case. You mentioned we wanted to create a new node, right? How do we do that? How do we create a new node? So we're going to create a -1. How do we create a new node? First declare a pointer. Okay, sure. Let's call it binary tree nodes temp. And then, how do you declare a new node? You've been doing it on tiles. New binary tree node. Okay, and it's cleaner if we just put the parameters directly. So, what value do we want to give it? What data? Negative level. What's the right pointer we want to set it initially as? So, we have a. It's 28. This was originally here. Okay, so we have a -1. Root is this pointer. Because we're passing it by reference. What should the children of -1 be? -1's left should be which one? The left should be 94, right? Because 28 was up here, 94 was down here. We want to put 28 at the missing child. So we would point the left. Let's see, the left at 94. And how do we get 94?
No.
Root left. Right, okay. Okay, how about the right? So what should the right of just root itself, right? Okay, this is temp. So negative level, root left, and then just root itself. Okay, what else do we have to change?
Root.
Okay, what do we want to change the root to?
Oh, maybe we don't need the pointer. We can just set root to the middle.
Just set root to temp. Okay, root to temp. So we set root, which is this pointer. We want to change that so that it's not pointing to temp. Okay. And then one more thing we have to fix.
I guess we can do root now. Root left. Or no.
Or maybe before that.
Yeah.
Before setting root to temp.
Yeah, we can do before that. We can say root left equals null pointer.
Okay, so root left equals null pointer. Let's try that. So before root was still, where's my red? Here. Before root was pointing here, and we're saying root left, set that to null pointer, so that changes this one. Now we say root equals temp, so that does this. Okay, great. This line is very important. This line over here. Okay, I think during this actual exam, I think like 70% of the students forgot this line. This line is essentially what's, if you forget this line, then you have like 28 still pointing to 94. That kind of messes up your tree. Let's see, you do need a temp variable here. So I don't think there's a way around just putting root here, because you have to insert this line between setting root equals to temp and declaring temp itself. Okay? How about the right side? Okay, it's the same thing, but just instead of to the left, you'd always just make it to the right. So here we change that to the right. Here we change that to right, and that's it. Okay. Okay, so that takes care of this part. After that, so no matter if we change the node or not, we should make the recursive call just to make sure everything below still works. Okay, so make full helper root left, and then we're going down one level, so level +1. Make full helper root right level +1. Okay. I think one more thing. This function returns an int, so that int is the number of nodes you're changing. So one way to do that, int sum equals 0. If we actually change to something, then we just add 1 to the sum, and then we just return the sum, either 0 or 1, depending on if we added a node, and then we add that to whatever the recursive call is going to do. Okay, and here, just return make full helper root. We start at level 0. Yeah, good point. So let's see. Yes, we need a base case. What would the base case be? If root equals null perturb, then return 0. Oh no. Don't I have to call level in the main function? I think I passed it 0, right? Let's see, if both are null pointers. So if both are null pointers, that's fine because when we make this recursive call, it's going to go into the base case next, and it's going to say it's null pointer. Yeah, so that's fine. Anyone see what the bug is? Let's see. Temp is equal to new binary tree node, negative level root. We want to set the root left, root itself. See, I'm concerned about this part. Let's try tracing through this just to see if it's right. What's wrong? Is it a seg fault? Parameters incorrect. Oh, okay. Yeah. Sorry. Did one of you mention this? Let's see. It should be -1, but it's saying 0. It should be, yeah. These are incorrect. The numbers we put were incorrect. So something here is wrong. Let's see. 1. Oh yeah, because the first level was 1. Okay. There we go. Great. Okay. I'll admit, when I did this question a couple days ago, I forgot this line. So if you forget this line, it won't work. Right. I think it might cause like an infinite recursion or something, because maybe not infinite recursion, but because this is still pointing to this, so your recursion kind of gets messed up. Okay, so we just remove that. That will work. Okay, so this is a pretty standard exam question. It's around this level of difficulty, so make sure you prep for these kinds of questions. Okay. The other problems I suggest that you do. Yeah, so here are like some really good questions. Zip is a pretty tough question. Yeah, zip is a pretty tough. I mean, you can just look at this. This looks kind of terrifying. This is zip. It was given a couple quarters ago. Remove kth leaf, I think, was in the fall. Yeah, this was in the fall. And then my personal favorite, the question that I got when I took the class was, there's one called remove file. Huh, maybe it's not here. Remove file. Here, remove file. Okay, remove file is really cool in that you're essentially treating a file system as a binary search tree. So this is like, we're saying that this file system you have is a binary search tree, and you want to remove files from it. Okay, this is a pretty tough question. So if you want to challenge yourself, make sure you're extra prepared in case Tyler throws you a curveball. You can try this question. All right. I'll send more practice questions as well. I sent a practice question on like how to deal with heaps. So like practice questions on heap traces, binary search tree traces. Those will certainly be on the final. Okay. All right. Yeah. So just a note: next week's section is required, and I really please come because I'll bring food or something. So please come. Also, I have this tradition. I've continued this for 2 years now. I take a selfie with all my sectionees. So if you don't want to be in the photo, that's fine. Just a note. I won't remember you if you're not in my photo. So that's your choice. And then yeah, I have a whole collection of photos, and I can show a history of all my sectionees. Okay. Yeah. All right. Yeah. Thanks for coming. Please show up next week. Remember, the final is in 8 days. Okay. It's coming up. It feels like we just got the midterm back, but the final is coming up. Please let me know if any questions. Solutions are here. Solutions are in the front. Make sure your name is on there. Okay.